Hello everyone, welcome to our lecture for recurrent neural networks. We will talk about the motivation for RNN, core concept, architecture, issues, and as always we would like to look at numerical example. The motivation for recurrent neural network or RNN, they are designed for sequential data. We have seen the neural networks that we studied earlier in the course. They kind of you give it the data and it responds with classification or regression result, but it doesn't have the concept of sequential data. On the other hand, RNN, they handle variable length input. They have some kind of memory that's very important. And that memory enables it to capture dependencies, relations across time. So RNN ideal for tasks like language modeling, speech recognition, time series analysis, anything that you have time steps with events or data that has relationship with the previous data or dependencies of the previous data and the following on data. So why do we care about sequence modeling? Why does it matter? Standard neural networks assume independent inputs, the one that we studied. On the other hand, RNN introduces the concept of time and memory, right? So time, it means that we have time steps. Memory, you are retaining information of what you have seen from the previous data. If we look at the so far what we have done, it's more of a static data. We give it the image, the neural network tells me the result, right? However, sequential data like text, audio, time series requires memory, memory to capture the previous steps. Take this, this is a very good example. Take this, let's say 2 words, not good. Good alone is positive. However, the not changes the sentiment to negative. So the sentiment of good depends on earlier word, which is not. So if I just capture only the word good, that reflects a positive thing. But because now I have captured an earlier data, an earlier word, which is not, now it's completely the opposite. Now that tells you why we care about memory, right? Why we look at the sequence across the time. Okay, so it's more, this is RNN is a solution for these sequential type of data. How do we do this? What's the intuition for RNN? RNN loops or feedbacks its output as memory, and that enables it to remember. Always feedbacks creates type of memory. In fact, we have seen this in designing of flip-flops and latches in our circuit design courses. Each step update the hidden state, because every data we kind of update a hidden state. So what's the hidden state here? It's the memory. This is our technical definition of RNN memory. We refer to it as the hidden state. Okay, so what's inside this hidden state? Simple neurons. Okay, What's the size of it? We'll talk about it in a few slides, but it could be 1 neuron, it could be 2. It is how many or how complicated your sequence that you want to capture, right? If you care about a sequence of 2 things, it is different than a sequence of 10 things, right? And things mean here the data. That hidden state evolves over time while retaining the context of the previous steps, which means every time you update your state and at the same time you capture previous knowledge. We can think of this hidden state analogy like reading a sentence word by word. Every word adds to your memory, to your understanding, meaning. At the same time, you are not losing the meaning of the previous words that you have read. Okay, so let's talk about this core concept. The core concept of an RNN is that we introduce step T. Step T. Why? Anytime we talk about sequence, series, we represent the current step with time t, the previous step as t minus 1. And therefore, you will see this loop here generated as hidden state, right? And captured in the next computation as t minus 1. And what I have here in front of me is the internal state in this represented in this box. Into it we feed in the current input and we feed in the feedback coming from the previous state. So 2 major inputs, the current input xt multiplied by certain weights and the previous state, right, multiplied by certain weights, and there is a bias here. That goes into an activation function, and we compute the current state, the current hidden state. That current hidden state, I can produce it. We will look at how we unroll this, but for now we will use it to produce the output. So we multiply it by certain weights, and we generate the output of the RNN. But the loop is doing its work every single time step. All right. Now, so RNN remembers by this loop because we create this here. We create the hidden state. And the hidden state is computed by multiplying the weight matrix, right? This is the input weights, right? You can see this here by the input, and the hidden state weight by the hidden state, the previous hidden state, plus the bias, and this goes to an activation function, which is tan h. Okay? Tan h, this is displayed here. It has a value between 1 and minus 1. Okay? Very similar to this sigmoid. Okay? Now, in terms of, as we have stated, in terms of the architecture, we have the key component here, the hidden state, which consists of 1 or more neurons. It computes, the hidden state is computed by this equation. And the second component in this architecture is the neuron that computes the output, right? A key question here, what is the hidden state size? I think we alluded to this before. It can be 1 neuron, it can be multiple neurons, it can be 2 neurons, 8 neurons. So what's the size? Well, here you have to gauge the size of the hidden state based on the length of the sequence. A sequence that you need to capture a sequence of 10 things probably require 10 neurons. A sequence, you want to capture events that crosses 2 time steps or 3 time steps, you probably want to have 2 to 3 neurons to save the history. Reduce, so there is this optimum number, and you have to do some kind of experimentation with the experience, but too many neurons not needed makes in the hidden state makes your design complex. Too few neurons in the hidden state makes your RNN inefficient, and it will struggle to capture the essence of the sequence. Okay, you need to do experimentation. You have to gain some experience in these things, right? So now, this hidden size, or the hidden state size, is a key parameter, very important parameter, and it controls the complexity of your design. How? Well, take a look here. You see this weight matrix here? So let's assume the size of this one here, X, is input size, which means it could be 1 data, 2 data, etc. And now you can see that the weights here, their size is hidden size times the input size. So let's just say, for example, for the sake of the argument, my input is single input. So you can see that the hidden size here, let's assume it's, for example, 8. So you see this is 8 times 1. If I change number of neurons here in the hidden state to 10, this will be 10 by 1. Okay, so it gauges the complexity of these, okay, the size of the neurons. Not only that, watch this parameter when this hidden state go back here. When it goes back, we multiply it by the memory weight. So this is the memory. What's the size of it? It's the hidden size times hidden size, which means if I have 8 neurons here, the size of this weight here, WHH, will be 8 by 8. Right? So it's very important you choose the size of the hidden state. It controls all these matrices for you. Now, finally, when we take the output of the hidden state and we produce the output Y here, we multiply it by WY, which is the output weights. And it is the output size. So let's suppose we have one output. So it's times the hidden size. So in our example, if we have 8 neurons, it's 1 by 8. You have a bias here, okay, which is a hidden size by 1. And you have also a bias here for the output, which is output size by 1. The key thing that we want to stress here is that the hidden state size controls the complexity of your RNN design, because it controls the sizes of all these parameters, which brings us back to the point that you want to select and choose the optimum size of your hidden states. An overkill size makes your design complex unnecessarily, and a small size will lead to a RNN struggling to understand your design. Okay. One thing we could do with the RNN is we can unroll them. Since I have a feedback here, an idea is we can take this design here, which is the hidden state and the output, and copy them here. Here's one copy, another copy, another copy, another copy here. And then have this feedback move from one cell to the other one. It's exactly like the carry chain and the carry ripple adder. Exactly the same thing. Okay, so you can see we start here with H0, which is an initial value. We produce here a hidden state, same size as the hidden state before, right? So if it is, for example, 8 neurons, you would have to send the value of 8 neurons to the next cell. And you produce another one to the next cell, and to the next cell, to the next cell. And you can see that all these sizes here, I'm sorry, all these weights here are shared. Okay, so we can unroll and we can share the weights. We don't have to have different weights. Now, some claim this is much easier way to demonstrate and illustrate the way the RNN works, but I want to just give you you know small warning here. If you take a design, right? Let's say, for example, a design, and you train it, then you unroll it, let's say for 4 cells, you might get different results, maybe close, but not identical, because there are few details related to the training of this one cell design with the multi-cell or unrolled design. Okay, so you might want, if you exercise with those in actual code, don't expect identical results. Okay. Okay, so the claim is this is much more elaborative and easier to understand to some folks. So another variation of the RNN is the unrolled variation. What's the choice of activation function? We have seen tan-H. Tan-H, from experience, it helps stabilizes the values because it bound them between -1 and 1. ReLU leads to exploding states because of the loops, and sigmoid is saturates faster. So people have seen tan-H performs very well with RNN. In terms of the loss function, you compute the loss at each step, and then you compute the total loss, which is the sum or the average over the entire sequence, the sequence that you care about. See, maybe your sequence is 3 items, so you have to sum or average the loss through those 3 items. Of course, when you capture here the loss, the total loss through the sequence, this allows the learning of the entire sequence. That's important. Okay, what makes the RNN different from the neural networks that we have seen before is that this notion of a sequence. Let's keep this in mind. That's why we have to slightly update the definition of the loss function. The back propagation, error propagates back through each time step. Training consider earlier memory influence. Here's the key. Long sequences make back propagation through time expensive. Not only that, but we end up having problems because the gradient get multiplied with factors. It has this multiplication inside it. If you have a parameter that has to go through multiple stages of multiplication, so if those multiplications are greater than 1, then these values explodes in their values. If you have the multiplications less than 1, then those values vanishes. They approaches 0. And this is one of the most important problems of the RNN, the vanishing or the exploding gradients. And that's what makes them very hard to train at some times, in particular for long sequence, because the exploding or vanishing it shows up very clearly in long sequences. Let's take an example here where we want to generate Fibonacci series. And what we did, we trained a network on a Fibonacci series, right? And at the end, we give it a 1. I'm not going to go through the details. When we train the Fibonacci series, we trained it on this on this series 0, 1, 1, 1, 2, 3, 5, etc. Then we gave it an input 1, okay, so that it will continue the rest of the series. So here's the output. It was capable of predicting the first output 1, and very close, okay, 1.31. 1.9 and 2, okay, 2.93 close, 4.57 point, and you can see it diverges slightly, but it was able to get numbers very close to the actual correct number. So we trained it on the sequence, it memorizes the sequence, and then when we gave it an input 1, it was capable of producing or reproducing the sequence based on what it learned and saved in the hidden state. Simple example, but with powerful performance, because it captures the essence of the sequence. There are other examples you can think of, but this shows you the capability of RNN, in particular for sequence and series type of data. And thank you very much. This is what I wanted to explain in this lecture, to summarize the ideas of RNN and captures the essence of this feedback type of a neural network, which has applications specifically relate to understanding sequence and producing sequences. Thank you very much. This comes to the end of my lecture for today.